Hello and welcome everybody to Technically Speaking, this final installment of our series on specialty drying systems. My name is Brandon Burton and I will be your host today as we take a deeper look at the technical drying systems that are used in water damage restoration. We've gone through a couple of previous series or episodes this year where we've taken a little bit of a look at some of the conversations around low evaporation assemblies and some of the other considerations that feed into when a specialty drying system might be necessary. So today we're going to take a look at those specialty drying systems themselves. So to get us started here, first a quick introduction for those that might be new here at Technically Speaking. My name is Brandon Burton. I am the Senior Principal of Industry Relations here at Cotality. I need to update that on the slide. I'm also the chair of the ANSI IICRC standards, and a lot of what I bring you here with Technically Speaking comes from that perspective, really talking about what our industry standards of care say about particular topics in the industry, and then translating that into some practical application. So with that said, a couple of quick housekeeping notes. Please remember that we do not use the chat here in Technically Speaking. We use the Q&A tool. So at any point, if you have a question during today's presentation, please open up the Q&A tool and drop your questions, any questions related to the industry, and we'll address those all in kind of an open hall forum at the end of the presentation. Just as a note for those that are joining live, the Q&A is a portion of the presentation that we reserve only for live attendees. So if you're watching this as a recording at some point in the future, you're missing out on the Q&A. The Q&A ends up being a really, really valuable piece of these episodes for me as well. So please drop those questions in frequently and we'll address those at the end. So with that said, let's take a look at specialty drying systems. We're going to talk a little bit about the IICRC's S500 first. We'll start off with that, and then we'll dive into the practical side of this discussion. In terms of specialty drying systems, the S500 actually doesn't have a lot. There's a significant amount of information, as we've covered in the last couple of episodes, about low evaporation assemblies. Also discussions about maximizing vapor pressure differentials when we're dealing with low evaporation materials and assemblies. So from a theoretical standpoint, the S500 most definitely touches this topic. Where the S500 doesn't get real specific is about the specialty drying systems themselves. For example, with dehumidification, we have our standard dehumidification that we use in industry. The most common is the low grain refrigerant, keyword being refrigerant, and the specialty systems being the application of heat and air exchange, the application of desiccant dehumidification. These are just a couple of the more specialized systems that we might deploy based on the circumstance. And the S500 doesn't really make that differentiation. When it talks about humidity control, it just generically talks about humidity control. When it talks about the use of a dehumidifier, it just generically talks about the use of a dehumidifier. The exception to that is in Appendix B. So if you've read the S500 or you're familiar with the S500, but you haven't kind of dug into the back of the document and looked at the appendices, the Appendix B does get into some discussion about differentiation between the refrigerant type dehumidifier, most namely the LGR, and the desiccant dehumidifier. So I'd highly recommend that. It's great reading. It gets into the different methodologies for calculation, whether you're talking about the simple, just solely class-based calculation method versus the more complex or detailed method that considers build-out density and outdoor weather and HVAC systems, et cetera, et cetera. So I definitely highly recommend that as a read. Having said that, understand that that's an appendix. It's not the standard. And the standard itself really doesn't say, you should use a desiccant in this situation, and you should use a refrigerant in that situation. It just calls out when higher vapor pressure differentials might be necessary. So we'll unpack that in the practical side of today's presentation. In airflow, there's a little bit of information about specialty drying systems. When you take a look at air movement and managing airflow in the project, there is conversation in the S500 about kind of starting at the most basic and getting a bit deeper, conversation about ensuring that you do get air movement across all wet evaporating surfaces, right? The airflow has to happen along all of those surfaces. It also calls out specifically that those surfaces may exist inside of cavities, they may be in interstitial spaces, and that airflow needs to be present in those spaces as well if moisture is present. And that is definitely a call out to specialty drying systems, because the only way to get air to move in an interstitial space or cavity is going to be through the use of either a specialty drying system or demolition, right? One of those two is going to have to happen. So we'll talk a little bit about what the S500 says about that as we dig in today. We'll also get specific into some of those those specialty drying systems that deal with that for us. Another specialty system the S500 does have some definite opinion on is filtration devices, most specifically air filtration devices, or AFDs. There is language in our S500, and we've really unpacked this language in great detail in an episode last year, but to provide kind of a high-level summary, when cleaning alone is not effective at dealing with dust and particulate and any other foreign matter that is of concern, or there are immune compromised individuals or high risk individuals that occupy the space, then the restorer may consider the use of one or more air filtration devices, to quote the standard. So air filtration devices definitely are discussed. Another context for air filtration devices in the standard is that when we are using these specialty interstitial drying systems or inter-air drying systems, that, like in the bullet just above this one, then we're drawing air out of these cavities and forcing that air to mix with the rest of the built environment. That's another reason why air filtration devices need to be considered, because we just don't know what's in that cavity. So those are two of the key areas in the standard that air filtration devices are called out. Those are three main buckets that we're going to dive into pretty deep today: dehumidification, airflow, and filtration devices. We're going to talk about all three of these. We're going to talk about them from a practical standpoint, understanding what they are, when we do use them, some best practices for how to use them to get the most out of these systems. So that's kind of the core of today's presentation. We'll also touch on at the end a bucket of what I call kind of other specialty systems, things like remote monitoring, for example, or power distribution devices and power management devices. So some other categories of specialty systems that I do want to touch on that we'll also kind of conclude with at the end of today's presentation. So that's the scope. That's what we're going to dig into. That's what the S500 gives us about some of these conversations. Let's start off by digging into dehumidification. So with dehumidification, when we talk about specialty systems, the primary conversation is about refrigerant dehumidification, which we see on the left-hand side of the slide, versus what we call desiccant dehumidification, which we see on the right. So starting off with the refrigerant over on the left, this is the most common type of dehumidifier that's being deployed in our industry today. Chances are probably 90 times out of 100, if not more, this is what you're pulling off the truck and wheeling into the property, plugging in and turning on. It's some form of a refrigerant dehumidification system. The most common type of those refrigerants used today is something we refer to as a low grain refrigerant, or LGR. And I'll explain a little bit about what that means in just a moment. But to understand when we would use one of these versus the other, we've got to dig a little bit into the technical behind how they operate so we can understand some of their strengths and some of their weaknesses. So start off with the refrigerant style dehumidification. Inside of a refrigerant dehumidifier, there is a refrigeration system. Not too surprising. A refrigeration system is the same system that you would find in a refrigerator or an air conditioner or something of the like, or a heat pump, but it has some really basic components. In blue, we have a coil system. It looks like the radiator on a car, kind of. And this coil system gets extremely cold. On the other side of that dehumidifier, we have another coil system that gets very, very warm, in some cases quite hot. These operate based on refrigeration theory, and I'm not going to get super deep into refrigeration theory. I'm just going to give you the really high-level details. What makes one cold and the other hot is basically a concentration of energy. You'll notice a little device underneath those two coils. This is a compressor or a pump, and what it's doing is it's pulling refrigerant out of the cold coil, the blue one, and making a really low pressure on one side, and it's forcing that refrigerant into the opposite end, the hot one. And the easiest way to understand what that does is just think about concentrating and diluting heat, true heat energy. If you take a sample of air the size of a softball. So just kind of imagine that for a second. You just got this piece of air out in your hand out in front of you that's the size of a softball, and that softball is 70 degrees Fahrenheit. That temperature that you're feeling is something that we call sensible heat. If I were to take that softball and I were to expand that softball to something the size of a volleyball, right, without letting any air or energy go in, just expanding that and causing the gas that's inside of that to expand over a greater space, what would happen would be the temperature you're feeling, the sensible temperature, would be substantially lower because I've diluted that heat over a much larger area. So what you're sensing is now a much lower temperature because of that dilution over that greater area. Same mass, greater area. We do the opposite on the other end. We compress, right? Now, there's more that goes on behind the scenes in that. I'm not going to dig into all of that. All I want you to understand for right now is that this refrigeration system, what it does is it makes one side very cold and the other side very hot. Now, on the cold side, we bring air in from the drying environment, and we introduce that air to that cold coil. So on my psychrometric chart, let's just kind of explore this by saying the air coming in that's in your drying environment is 80 degrees Fahrenheit at 50% relative humidity. So that's what I have plotted here on my psychrometric chart, 80 degrees Fahrenheit and 50% relative humidity. What the refrigerant dehumidifier has to do is to cool this air down below its dew point. So let's add a line here. This dotted yellow line that's going across that intersection on my psychrometric chart. If you look to the right, you'll see under the column that says DP, that stands for dew point, that the dew point of that air is 60 degrees Fahrenheit. What does that mean? That means that if I can cool this air to below 60 degrees Fahrenheit, then I can start to see condensation as a net overall result. I can start condensing the moisture out of that air. And that's essentially what the refrigerant has to do. It has to take that air and cool it to a temperature that is below its dew point. Not just a little below its dew point, a lot below its dew point, so that we can get lots of moisture to sweat out of that air, to condense out of the air. If you look towards the left on the psychrometric chart, you can see that happen. Right, so start with your 80-degree temperature line in blue, and then follow that dotted yellow line to the left. And that notice that as we move to the left, at some point we start running off of the psychrometric chart. That happens at 60 degrees Fahrenheit. Kind of let that sink in for a second. The dew point of that air is 60 degrees Fahrenheit. That tells me that if I cool to 60 and below, I'm going to start running off of the psychrometric chart. As we continue to go below 60 degrees Fahrenheit, we can see that now the amount of moisture that is in the air at 80-60, or 80-50 rather, no longer fits in that air. That's the moisture that begins to sweat out of the air. And the more we cool below dew point, the more condensation we get. Now, there's limitations with this. There are lots and lots of limitations with this, with a refrigerant dehumidifier. First of all, in order to get good dehumidification here, look at what I'm doing to the air. I'm cooling at 40 degrees Fahrenheit. That's a lot of cooling as that air passes through that refrigerant dehumidifier. All right, that takes a lot of energy to create that much cooling inside of that refrigeration system. And most refrigerant dehumidifiers are just not real good at doing that. You know, they'll give you a few degrees of cooling below dew point, but it's really hard when I've got to cool 40 degrees Fahrenheit and to get it all the way down to that temperature. What is even more limiting is that I'm getting down to 40 degrees in this example. I'm getting good dehumidification. But if I lower that 80 degrees a bit, or I lower the humidity a bit, I have to cool the air down below 30 in order to get good dehumidification. And this causes the refrigerant dehumidifier to ice up, right? So if that cold coil is less than freezing, then the water that collects on it is going to collect as an ice. And when it collects as an ice, then I've got to shut everything down and go through a defrost cycle. Right? And that happens as soon as my air gets down to about a 32-degree dew point temperature, right? I have to freeze the moisture out of the air. And that's where the limitation on even low-grain refrigerants really starts to kick in, is when we get into these defrosting cycles. And you've probably run into this. You go in to monitor your dehumidification systems, you take your thermal hygrometer, you take a temperature and humidity reading, and you say, you know what, this doesn't make any sense. The air coming out of my refrigerant dehumidifier is cool and very humid. Right? If any air is coming out at all, depending on the type that it is. So that's a very severe limitation on the refrigerant dehumidification system. So with all of that said, these are the limits. The refrigerant dehumidifier has a limitation based on the fact that it uses condensation to remove moisture from air. It's very dew point driven, and the lower the dew point of the air, the more severely limited the dehumidifier is. It's very efficient in high humidity, right? When humidities are super high and water would sweat out and make a puddle, even if you put a glass of water on the counter, and just that cool surface of the glass would create condensation. Refrigerant dehumidifiers are great, right? They're very energy efficient in high humidity. The LGR component to them helps, and to give you a really simple explanation to what the LGR component is, think of a refrigerant dehumidifier this way. Think of a sponge for a moment, and I take a sponge and I put that sponge down into a bucket of water to absorb moisture, right? That's kind of your air in a drying environment soaking up moisture from a wet surface. What a refrigerant dehumidifier does is it takes the sponge out of that bucket and puts it over a drain or a sink and squeezes the sponge, right? When I squeeze that sponge and lower the capacity of the sponge, water falls out. And that's what's happening on that first coil. The air is being cooled, which reduces the energy to support moisture. It lowers the capacity, if you will, in simple terms. That wrings moisture out of the sponge. What an LGR does is it then folds that sponge in half and squeezes it again. There's a second cooling mechanism that happens inside of an LGR, and I'm not going to run through the technical details of that today, but in essence, that's what's happening. Is the low-grain refrigerant leverages some efficiencies that already exist in that refrigeration system to cool the air not once, but twice. So that I get more water out of that sponge. So I produce a much drier air on the exhaust. But even with LGR, you're still limited by the refrigeration limitations, right? If that coil is down around 32 degrees, we're going to get ice. And if we get ice, we got to shut down. And when we shut down, we're not really dehumidifying at that point, right? We're just trying to get some ice off the coil so we can get back into operation. So that's a refrigerant. And that's a limitation that we can live with most of the time, right? When we're dealing with materials that let go of moisture relatively readily, the refrigeration system works perfectly fine with porous materials, highly porous materials, warm environments where evaporation is happening rapidly. We can get airflow across all of our wet surfaces readily. Then generally, we don't see any limitations there that really start to get in the way. Now let's talk about the desiccant dehumidifier. First of all, the only thing really difficult about a desiccant dehumidifier is spelling it properly. It's 2 C's, not 2 S's, right? Desiccants are actually very, very simple machines. They're far simpler than refrigeration machines, which makes one question sometimes why they're more expensive than refrigeration machines. But they are actually far simpler machines. They work on the process of sorption, right? Now, I say sorption without saying ab before it because there are desiccants that absorb and there are desiccants that adsorb. And we can talk a little bit more about that as we get deeper into this. But for now, what a desiccant does in really, really simple terms is it uses a material that has an extremely low chemical vapor pressure. Usually silica gel, sometimes lithium chloride, the stuff that you get in the little packet when you buy a pair of shoes that says do not eat, right? That's what's inside of a desiccant dehumidifier. And generally the way that they put this in a desiccant dehumidifier is you'll see kind of as the core of my drawing here, this big round rotor. This rotor has on the inside of it a material that I'm going to describe this way. I want you to imagine for a second that I'm taking a corrugated cardboard box and I'm going to cut the corrugated cardboard into strips that are about 3 inches wide, and I'm going to roll that corrugated cardboard up until it gets bigger and bigger and bigger and makes this rotor. Now, the corrugations are passing through, just like my blue arrow here, they're passing through perpendicular to the rotor. Now, we're going to paint all of that corrugation or coat all of that corrugation with silica gel, which is basically like a chemical moisture magnet. It has a chemically low water vapor pressure. Now with that blue arrow, we're going to take air from the built environment and we're going to run that air directly across this rotor. And what happens as the air passes across this rotor, as long as it's not saturated, the rotor is going to collect water molecules from the air, regardless of how many are present. Regardless of how many are present. Doesn't matter what the dew point is, doesn't matter if you have high humidity or low humidity. As air passes across that rotor, water molecules are going to collect on that silica gel surface. It's kind of like taking a magnet and dropping a magnet into a 5-gallon bucket full of thumbtacks, right? That magnet, when you pull it back out, if there are metal thumbtacks in that bucket and it's a magnet, you're going to pull thumbtacks out, right? Whether there's 1,000 thumbtacks in the bucket or there's one thumbtack in the bucket. And that's kind of the principle of a desiccant dehumidifier. It doesn't really matter how humid the air is, a desiccant dehumidifier is going to dehumidify for all practical purposes. Now, the limitation for a desiccant dehumidifier is that that silica gel can only hold on to so much moisture, right? If I just keep passing wet air through it, then eventually that silica is going to saturate. It's kind of like taking the magnet and dropping it down into the 5-gallon bucket and coming out with 20 thumbtacks. If you don't get rid of the thumbtacks and you just drop the magnet back down to the bucket and pull it up again, you could do that till you're blue in the face. You're not going to get any more because the magnet's capacity to sorb, if you will, to absorb or adsorb that metal is at saturation, right? I've already extended the capacity of the strength of that magnet. So we have to reactivate the silica gel. Now here's how the reactivation happens, and this will help us understand the strengths and limitations of this machine. Notice the arrow that I have on that rotor and how that rotor is turning continuously. You know, it turns relatively slowly. It could take a minute or two sometimes, depending on the type of desiccant for it to make one revolution, but it's turning relatively slowly. As that rotor turns, the portion of the rotor that was sorbing the moisture, absorbing or adsorbing the moisture, is going to pass into a reactivation chamber. That reactivation chamber has a heater element, and we take that heater element and superheat an airstream and pass that heated air across the silica. We basically bake the moisture back off of the rotor. Now take a look in the very lower right-hand corner. You'll see my little side profile of a desiccant. This is the air that has usually ductwork attached to it, and we duct that air to the exterior of our drying environment, hopefully to the exterior of the building, because this is going to feel much like the air coming off of a clothes dryer exhaust. It's going to be warm and it's going to be humid, right? Which in some cases, so humid, the water will actually start to condense inside of that ductwork, depending upon the amount of moisture that you're removing and depending on how cold the duct is. Now that reactivation process gets the rotor to be dry again. The problem is that as the rotor comes out of that reactivation process, the rotor is extremely hot, right? So we continue to rotate the rotor and we come out of that reactivation chamber and we pull a separate airstream across that rotor to cool it back down. Now what's kind of cool about a desiccant is how energy efficient certain types are. This is the one on my screen here is what we call a purge style, but this green arrow that is being used to cool the rotor down, that air is picking up heat. So we use that heat before we go into the heater to get superheated to bake the rotor dry, right? Kind of a cool efficiency there in engineering. So with all of that said, with this operation of a desiccant dehumidifier, when would I use one and how would I use one? So a couple of notes here. First and foremost, the first thing to understand is that a desiccant dehumidifier is generally not the right type of dehumidification to use, especially in the early phases of drying when you're dealing with a lot of porous and highly porous materials, when you're dealing with a high degree of saturation, when you're dealing with rapid airflow immediately over damp surfaces with high evaporation rates. In other words, it's not a very effective system when we're talking about a class 2 water damage or a class 3 water damage, generally speaking, with these higher evaporation rates. And the reason is because that rotor can only hold on to so much moisture at a time. And what's going to happen is you're going to hit the upper end max performance that the desiccant has, and everything above that is just going to pass right through the rotor. Whereas with a refrigerant, the more moisture there is in the air, the faster it's going to condense, right? There is no max end on a refrigerant. Right? When you look at a refrigerant dehumidifier and it says it's rated at 100 pints per day, well, that's at 80 degrees and 60% relative humidity. Give it 80 degrees and 90% relative humidity, it's going to give you far more than that. Give it 80 degrees and 100% relative humidity, it's going to give you even more, right? So there is no max end. The wetter the air is that you feed a refrigerant, the more condensation you're going to get. So in really high evaporation rates, refrigerants shine. When we're dealing, however, with a class 4 drying scenario, or we're dealing with a class, what started as a 2 or a 3, but now we're dealing with some residual areas that are drying much more slowly, and we're 4 days into the drying process or 5 days into the drying process, and the existing temperature and humidity that I've created is no longer giving me any meaningful progress, right? Now we're technically kind of at a class 4 portion, if you will, of what initially started as a class 2 or 3. these are the areas where the desiccant really begins to show where its true colors are and where it can shine, because it can take your low vapor pressure that you've created and drive that vapor pressure even lower. Another area where desiccant dehumidifiers really shine is understand what's happening on the bottom half of this rotor. You know, we dehumidify on the top half, but on the bottom half of this rotor, we are baking the rotor dry with electric heat, and then we're cooling the rotor back down again with a separate intake airstream. Okay, that cooling process, the more efficient that cooling is, the sooner the desiccant dehumidifier is going to start actively collecting water vapor from the air again. So the cooler the air that you feed the desiccant dehumidifier, the more efficient it will become. So this is another area where desiccants can really excel, is if you have the means to provide preconditioned air, cooled air to the intake of a desiccant dehumidifier, you're going to notice a significant boost in their performance. Now, whether that's because there's an existing air conditioning system that is operating within the structure, or there is cooler air that is available outside the structure, in either one of those cases, the desiccant dehumidifier can see a significant boost in performance if you pre-cool that incoming air. So that is the desiccant dehumidifier versus the refrigerant. And the really simple with desiccants and refrigerants is that a refrigerant is your 9 times out of 10 go-to on your class 2, your class 3 water damages. Your desiccant dehumidifier should be being leveraged much more commonly on a class 4 water damage. Don't see it used nearly often enough. It's also a finishing tool when you're dealing with those projects where you have stubborn areas of the drying process. It's one of the ways that we can force the drying to continue at a greater rate using an even lower vapor pressure when you have these systems available. All right, so that's refrigerants, desiccants, and an overview of when to dive into each. Quick reminder, if you haven't done so already, if you have any questions, drop those into the Q&A tool. We will have a town hall session here at the end. I just want to give a quick shout out to Ivy, John, and Wesley for dropping some things here into the Q&A. And it looks like hopefully those audio issues that a couple of folks were having have been resolved. If anybody could just drop me into the Q&A, just a quick 5x5 that you are getting audio, so I make sure that's resolved, and I'll keep an eyeball on that while we continue to progress here. So the next section I want to jump into for specialty drying systems is on airflow. In the air movement category, things can get a little bit more complicated than they do with desiccant dehumidifiers in terms of just the options and the choices that are out there for specialty drying systems and airflow. So to help us kind of unpack that and break that down, I want to talk about specialty drying systems and airflow in 4 general buckets. One bucket I'm going to call the high power dryer. This is your standard carpet dryer, the age-old snail shell carpet dryer, turbo dryer, if you will, centrifugal blower, but it has a much bigger motor in it, generally a 1 horsepower instead of a 1/4 or 0.4 horsepower motor. That's the HP dryer. You'll know that you grabbed one because your arm's going to come out of your socket when you go to pick it up because you're used to something that weighs half as much. All right. The next bucket is something I'm going to call the true vane axial. We have a lot of axial air movers that we use in our industry, but there is also what we call a true vane axial, or fireman's fan. This isn't your ACE or your dry your Force 9 or some of these others that we have out there that we use for just topical airflow across wet surfaces. These are ductable axial fans. They have a duct ring on the inlet, a duct ring on the outlet. They sound like a jet engine when you turn them on. They spin at a really, really high RPM and typically have a very aggressive blade. So that's a true fireman fan or true vane axial. So we'll talk about those as specialty drying tools. The next one down is actually called a bouncer blower. It's the blower you would see in behind those big castles that the kids jump around on at the fair, right? It's called a bouncer blower. In our industry, one specific model of this is called the Air Wolf. And then the 4th bucket that I want to talk about is what I call the true inter-air drying system. There are 2 makes of this in industry today that I'm aware of. One is the Dry Force, the other is the Inject Dry. So we're going to separate out into these 4 buckets. And as we separate in these 4 buckets, to understand their differences and when I would use one versus another and how to apply those systems, we've got to understand the technical side of their specifications. So I'm going to break those specs into 3 categories. One is CFM. How much air do they produce? Just free air. How much do they produce? The second is static pressure, which is a critical specification when it comes to specialty drying systems. Static pressure is the ability, in simple terms at least, it's the ability for the air mover to overcome resistance to airflow. All right, that's what I'm referring to by static pressure. Thanks, by the way, to those that are letting me know you can hear and we have sound. I appreciate that. The third category for specification is power efficiency. All right, so if I score it high here, it means it's really energy efficient. If I score it really low, it means it's a power monger, right? It's just sucking a lot of energy from your available power inside of the drying environment, which to me is a huge red flag for drying systems, because if we're dealing with anything more than a couple hundred square feet of wet area, sometimes the number one limiting factor to how I can dry that structure is my available power infrastructure. So I'm always very, very aware of how energy efficient my drying systems are, because I can shoot myself in the foot real fast if I start using high amp equipment in the drying environment. So those are my three specs: CFM, static pressure, and power efficiency. All right, so let's take a look at the first one here. The first one is the HP carpet dryer. The HP carpet dryer was kind of our industry's first inter-air drying system. All right, it's been in the industry longer than I have, and I've been in the industry for a long time. When I came into the industry, they were made of metal and they were furnace fans that were put inside of a metal housing. Then they got rotationally molded and then they got injection molded, but they're still out there and they're still being made. The CFM on these is pretty high. Generally speaking, an HP carpet dryer is going to produce between 2,000 and 3,000 cubic feet of air per minute. All right, so a very significant amount of airflow. The static pressure on them is decent. Usually the static pressure on an HP carpet dryer is going to be somewhere between 2 and 3 inches. And I'll explain what that means in the context of the other ones here in just a second. For right now, just know that 2 to 3 inches is decent. That high volume of flow is going to have the ability to force its way through attachments, through ducting. You could float a really, really big carpet with one of these. All right. The power efficiency is not great, though, because it's got really good CFM and decent static pressure. The trade-off for that is they draw a lot of power. Usually an HP carpet dryer is going to be around 9, 10, 11 amps. That means that it's pretty much going to consume an entire 15 amp circuit all by itself. Right. And sometimes that 15 amp circuit is all I've got for 3 or 4 rooms. Right. So one of these on that circuit is going to pretty much tag that circuit out from me being able to run much else for drying equipment. And again, that's a big red flag for me. I would still use these in certain circumstances, and I'll show you where here in a little bit. But generally speaking, I do not like the energy efficiency. Let's move down to the second one. The second one is the true vane axial, the fireman's fan. What's really interesting about the fireman's fan is that the fireman's fan is, first of all, outstanding for airflow. That's what it's designed for, right? You're going to look at 3,000 plus cubic feet per minute, typically coming off of these free air. They're also going to have a really good amount of static pressure, 3.5, 4 inches of static in some cases, depending on the design. And the reason for both of those being exceptionally high is what this is designed to do. What it's intended for is a safety fan. It's designed to take a really high volume of air and evacuate that air from a confined or contaminated or otherwise compromised space and replenish that with fresh, breathable atmosphere at 10, 11, 12, 13, 14 air changes per hour, whether that's after a fire, and we're trying to evacuate all of the carcinogens and the irritants that are inside of a space and evacuate all of that from the air and replace it with breathable atmosphere. Or if I'm working down in a manhole and I need to get fresh air down underneath the street through a manhole and supply breathable atmosphere while I'm working down in that environment. That's what these things were designed to do. And because they're designed to do that, they do a great job of doing that for us in crawl spaces. They do a great job of doing that for us if I'm trying to install a really aggressive open drying system in a structure or a space. They also work pretty well with other types of attachments on them. And there are some manufacturers that actually make smaller attachments that look like a plug that you would put on the end of this that reduces that air down to several 2-inch hoses for injection type drying or evacuation type drying. Again, the trade-off for that is because we have really high CFM and really good static pressure, the trade-off is they're not really energy efficient. Again, we're taking a look at 10 amps, 11 amps, somewhere in that neighborhood, really high amp draw. So when I use these, I have to use it because that's exactly what I need. It's high CFM at really high static pressure because I'm going to completely and totally take up an entire 15 amp circuit when I plug one in. The next one down is the bouncer blower. And this one's interesting because it starts to get for the first time into a little bit more of a specialized balance in inter-air drying systems. It's got a little lower CFM. It's only generating about 1,000, in reality about 700, 600, 700 CFM, but it produces that moderate CFM at a really high static pressure. We get a static pressure here of about 7 inches of static pressure. Now, what I want to, this will be the first time I'm going to give you a bearing for what static pressure means. Think about what this blower is designed to do for a second. It inflates a castle, right, or whatever other, structure it's going to look like, that if you throw in 15 kids, they can jump around and bounce around inside of this inflated, vinyl enclosure, and the static pressure of 7 inches is enough that they can stand on that and it won't deflate at 7 inches of static pressure. So just think about the power of 7 inches of static pressure for a moment, and then think about taking that off of a castle, right? And instead plugging it into a wall cavity, right? The amount of static pressure there is high enough that either air is going to move through that cavity or the cavity is going to inflate. Both are entirely possible, by the way. All right, so that's what 7 inches of static pressure can do for you. Now, because we sacrifice the CFM a bit to get the higher static, notice what happens. The power is not all as energy efficient. I meant to make that 3 and not 1, by the way. I moved that in the wrong direction on my slide. But it's slightly more power efficient than the first 2 that we talked about. All right, generally, a bouncer blower is going to be about 6 inches or 6 amps or 7 amps, somewhere in the neighborhood. So our amp draw comes down a little bit because we're sacrificing some of that CFM. So we get a bit more energy efficient there. I apologize for the error on my slide. Now, finally, last but not least, let's get into the true inter-air drying system. This one I did mark right. The true inter-air drying system gets into the true specialty of specialty systems, if you will, with airflow. Notice that the CFM is extremely low. A true inter-air drying system is only going to produce about 100 to 150 CFM. Really, really low on CFM. Where it's going to specialize is in exceptionally high static pressure. The static pressure on a true inter-air drying system is going to be somewhere in the neighborhood of about 20, 25 inches of static, all the way up to about 50 inches of static. Now, at 7 inches of static, what I inflate you can stand on, imagine what I can do with 50. Okay, and just kind of let that sink in for a second. These are designed specifically to ensure that the amount of air that they do produce, which isn't a lot, but the amount of air that they do produce is going to move, right? If there is any opening whatsoever that is larger than the molecules that make up air, air is going to move through that opening. So that's the true specialty of the specialty type systems. And the part of the reason why I wanted to give you this comparison between all 4 of these is that I'm going to get into 2 examples here for application. One is the HP carpet dryer and the other is the inter-air drying system. And I wanted you to understand kind of the reason why I would choose one in one case and the other in the other case, based on this different balance between CFM, static pressure, and power availability. Okay, so with that said, let's go ahead and roll into a couple of examples here. I'm going to start with the true inter-air drying system. And the example that I want to get into is an example that I've really been trying to create more and more awareness for in the industry because I think it's one of our great missed opportunities in restoration. We've talked about it a little bit in some prior episodes with Technically Speaking, with the use of mat systems and hardwood floor drying, even as recently as an episode this year. But what we didn't get into is some of the more finite details of that installation and what that looks like. So first, let's talk about what we are going to apply this to. Here I have a very specific layout of a hardwood floor in the kitchen area. We've got an area at kind of the upper end of this schematic that shows us a sink and a stove here, maybe a refrigerator. We've got an island cabinet that's out in the middle. Then off to the left, maybe a pantry cabinet or whatever that is. We can see that our hardwood flooring is running top to bottom, right? So that's the direction of my hardwood flooring planks. We can see all the individual planks that are installed there. So keep all of that in mind as we kind of roll through. Now, the way that this system is intended to work, I'm going to give you a little bit of a blow up of the hardwood floor here in the upper left. The way this system is intended to work, you can see a subfloor at the very, very bottom. On top of that subfloor, we can see our tongue and groove hardwood planks. At the bottom of those hardwood planks on the underside, you can see what we call the flutes. The flutes are an area underneath the hardwood that has been milled out. So we have a little bit of a recessed area there. And the intent behind those flutes is to put less of the hardwood in contact with the substrate. So when there's moisture transfer, there is less wood that is expanding and contracting and less dimensional change. That's the reason for the flutes that are on the bottom. But the flutes are an opportunity in the drying process. The way the mat system is intended to work, in this little blow up that we have here in the upper left, the mat is that orange area that we see on top of the hardwood flooring. On top of that mat, there is an area to connect a hose that will connect to my inter-air drying system. We pull on that hose, right? We create suction with our inter-air drying system, and that suction causes air to come up between the boards in the tongue and groove assembly. Right, so we're extracting air through that groove on that tongue and groove assembly. Because we're extracting that air is then being removed from underneath the hardwood floor and creates a negative pressure underneath the hardwood flooring planks. That negative pressure causes a pathway for airflow through the flutes. So air is drawn from outside of the mat area under the floor to the area underneath the mat, then up through the tongue and groove joint, and then is extracted by the blower and blown most likely outside. And we can talk about that more in just a second. Now, to compensate for the air that is moving underneath this floor, and here's the key, there has to be somewhere for air to travel down and underneath the floor. And one of the most common mistakes that's made when installing any form of inter-air drying system, it doesn't matter what type it is that we have to understand that there has to be a pathway, right? That pathway has to have an inlet to allow air to enter, and then the side that we're pulling air from. So to imagine this for a second, I want you to take another real quick mental field trip with me. I want you to imagine a coffee straw, all right? You're going to take one end of that coffee straw and you're going to put that in your mouth, right? And then we're going to suck on or inhale on one end of that coffee straw. Now, because the coffee straw is really tight, right, the air flow through that coffee straw is going to be limited, but we're going to get air to flow. Now, I want you to imagine putting your finger on the other end of the coffee straw. It doesn't matter how hard you pull on that coffee straw, right? The pressure no longer matters. If the pressure does not result in flow, then air movement has not been established and drying will not occur. So the only way for this mat system to work, the mat is like your mouth on one end of the straw, right? We're creating suction on one end of that straw, but that suction by itself is doing nothing. The suction only is effective if it results in flow. And it will only result in flow is if you keep your finger off of the other end of the straw. So how do we keep our finger off the other end of the straw? To understand that, I'm going to put these mats now on the hardwood floor. Notice my placement and how my placement is very intentional and it's very strategic. The first thing I want you to understand about the placement is that my mats are perpendicular to the planks. Now think about the reason why for just a moment. The mat is creating suction. That suction is going to result in flow through the flutes. The flutes are parallel with the boards. If I'm perpendicular on the floor, I will affect more flutes. Every mat will have a larger effective footprint because now it is causing a pressure or negative pressure on more flutes underneath these boards through all of the tongue and groove joints that are underneath the mat. That's the first thing I want you to observe. The second thing that I want you to observe is that none of my mats are touching each other. If I place my mats so that these long edges are in contact with one another, that's the same as you putting your finger on the other end of the straw. In addition to the negative pressure that's pulling air up through the tongue and groove joints, I need to allow the positive atmospheric pressure to allow makeup air to go down through the tongue and groove joints between the mats. Now that distance that you want to leave between these mats is going to vary. right? And I'll give you some pointers on what I've experienced for what that distance should be. If I am dealing with a water damaged floor that was finished on site, so boards that were installed without any finish on them, they were then sanded and finished on site. That finish is going to be a much greater seal on that floor than a floor that was pre-finished. A pre-finished floor is a floor where you buy it and the finish is already on the boards. Then you install that tongue and groove assembly and apply no additional finish. That flooring is going to allow for more airflow between the boards. The greater the opportunity for airflow, the tighter these mats can be to each other. The harder it is for the makeup air to get down between the boards, the further apart they should be. The closest I would ever install them is 2 to 2.5 feet. The furthest apart I would ever place them would be about 4.5 feet apart, depending upon how tight that installation is. Okay. Another way that you can gauge how tight the installation is by how much cupping has occurred. On a hardwood floor where there has been a significant amount of cupping and expansion, generally you're going to start to see some areas between the boards where it's very obvious that air is going to move down pretty readily because of the distortion that's occurring on the floor. It's also an indication there may be some permanent damage on the floor. Not a topic we're going to dig into today. Definitely had an episode on that last year where we dug into that pretty deeply. All right. So that's the second point I want to make is the distance between these boards perpendicular to the mats, the length of the floor, anywhere between 2.5 and about 4.5 feet, depending upon the tightness of that floor. Now, between the mat's short sides, all right, so when I go between one mat and move across perpendicular to the next mat, so the two short ends of those mats, that distance never needs to be more than about 2 feet apart. All right, because the air is not moving nearly as much in that direction because that's opposite of the direction of the flutes. Okay. Now that's based on my practical experience of installing mat systems on hardwood floors. I've gone through the process of restoring hardwood floors with mat installations on, I don't know, the 400, 500, different projects when I was active in doing so. And that was, from my practical experience, what I found to be most effective. Now, last point I want to make on this slide before we move off of it is one other advantage that you can take in how to install these is understanding how to plumb these different mats together. Your inter-air drying system, if you're using a dry force specifically, somewhere in the neighborhood of about 5-6 mats is about the most I would run off of that blower. If you're using the Inject-A-Dry, they make a couple of different models. They're smaller model. I would again run 5, 6, 7 mats somewhere in that neighborhood. But if they're using their large HP version, their HP 60, I believe is the model name on it, you can run more mats than that. You can run 9, 10, 11 mats off of that larger system. Again, just based on my practical experience. Now, in terms of plumbing them together, what I would do to get the best efficiency is to put my blower in the middle of my chain of mats. So take your eyes to the mats that you see running between the sink and the island counter, right? So you'll notice there's one small mat kind of up by itself in the upper left of that floor. And then we have a run of 4 mats that go right in between the island counter and the sink and the stove. My blower would be right in the middle of those mats. And then I would tee my hose and run in both directions. In other words, draw evenly from both sides. Don't run your blower and then run 20 feet of hose so that one of your mats is 20 feet away from the blower and one of your mats is only a foot away from the blower, right? Put your blower in the middle of the installation so you get a more even distribution of the power of that blower across the totality of those mats, okay? All right, so that's an application of the inter-air drying system. The other application I want to talk to very briefly with inter-air drying systems is the HP dryer. Sometimes the installation where you need an inter-air drying system is not as tight as a hardwood floor. Sometimes that installation, and I'll give you kind of the extreme, is a wall cavity where there is electrical that is running across that wall cavity and the studs are steel, right? And have a bunch of knockouts and openings that allow for very ample and easy airflow from one cavity to the next. In an installation like that, where that's what I'm trying to dry with a specialty drying system, it doesn't make a lot of sense to focus on an inter-air drying system that doesn't generate a lot of airflow. It focuses on high pressure. You don't really need high pressure because there's not a lot of resistance. It's like getting rid of the coffee straw and replacing that with a 7-Eleven Slurpee straw, right? The air moves much more easily, so you don't have to pull or blow as hard to get a lot of airflow. So in a case like that, you want a blower that's got the capability of delivering a lot more airflow, but it still needs to be able to do that through an attachment. So the attachment here that I'll talk to is a turbo vent. There's a couple of different styles of these turbo vents that are out there. In this particular case, probably what I would lean on is the turbo vent that attaches to the snout of your air mover, then reduces that to 3 4-inch ducts that go out to additional 2 3-foot wide turbo vents. So I'd have one blower powering multiples of these vents. The first step would be to remove the base trim from the assembly and then give myself an access point at the base of this cavity. That access point doesn't need to be any bigger than what will be covered up by the base trim when I put it back in place. And again, because there's electrical running through these cavities or these are metal studs and there's lots of knockouts, I don't need to use the more complicated low CFM high static pressure blower. Your standard run-of-the-mill 1 horsepower blower with an attachment that lets me address 20, 30 linear feet of wall with a single turbo vent setup is going to give me significant wall coverage with extremely high rate of flow that is not going to be resisted based on that installation. Now take the other side of that coin. If this had no electrical, if this was an exterior wall cavity, it was an R2000 rated home where the drywall was glued to the studs, the insulation is an expanding foam, right? I'm giving you all the scenarios I can to express that this is a really, really tight wall cavity. Then in those cases, that's when I would lean on the higher pressure blower, okay? Now, with all of that said, I would not use an inter-air drying system on this cavity unless I have data that shows me that the surfaces are wet inside the cavity, right? And this is the reason why we don't use inter-air drying systems automatically when we have a wet wall. We've got to think logically, where did the water come from? How did this wall come to be wet? If the water migrated across the floor at a depth no greater than the carpet and cushion, which is lower than the height of a wall plate, and then simply wicked up the drywall, then my first attempt is going to be drying it from the inside surface, right? If that's not effective, then I will get more effective or more aggressive with my means for affecting drying. Now, if this was a basement and we had some standing water and the water depth was 3 or 4 inches, then I know I have wet surfaces inside the wall cavity because that standing water is higher than the depth of my wall plate. Or if water originated from overhead, or if water originated from inside the wall cavity. So these are all reasons why I would automatically begin with either some disassembly or the use of an inter-air drying system, okay? All right, so last main topic here I want to touch on is filtration. Again, a quick reminder to drop your questions into the Q&A. Filtration may be relatively brief. Air filtration devices are discussed in the S500. The general statement is that they may be used. If you're familiar with the S500, may means permissive. It means that the restorer has the ability to make that determination based on certain criteria. The criteria that are given around air filtration is when cleaning alone is not determined to be effective at removing the soils and contaminants that are of concern, or when there are immune compromised individuals that occupy the space, or there is an active process of demolition that is occurring that is creating dirt and dust, and we're trying to control that. For any of these criteria, an air filtration device may be used, one or more. The only other criteria that is provided is when you are evacuating air from a cavity using an inter-air drying system, and that air has to be dumped back into the living space for whatever reason and not vented outside, then an air filtration device may be used there, or some sort of filtration system at the least. When we're using air filtration devices, I'm going to give you a couple of pointers on application. If I'm using an air filtration device during a process where I'm not yet actively drying the building, I'm just using air filtration to control dust in the environment. Maybe I'm doing demolition, maybe there's other processes occurring during stabilization, and we have not gotten to the point where I've put in a bunch of air movers, then at the very least, install your air filtration device so that its intake is in one room of your work area and its exhaust is into another room of your work area. This forces circulation and will dramatically increase the efficacy of your dust control. Don't just put it in the middle of one room and turn it on when your work area is comprised of multiple rooms. Now, if it was just one room that you're working in and you've got that closed off and contained, great, put it anywhere, right? But if you've got multiple rooms with barriers that restrict airflow, then at a very minimum, intake from one room, exhaust to the next to force some air exchange through that space to help with your dust management. Now, even better, install the air filtration device in one room of your work area and the exhaust into the opposite end of that workspace. So if you're dealing with all of these rooms and there's dust concern in all of these spaces, then one of the best ways to ensure you have good dust control is to have an intake at one extreme end and an exhaust at the opposite extreme end. Then the air will migrate back towards the intake and continue the cycle over and over again. This is exactly how a forced air system is engineered, right? We have an intake at one part of the structure and then exhausts all over the structure to create good circulation of the air throughout the space. So engineer your supplies and returns, okay? Even better yet, if you need multiple air filtration devices, depending on the size of the space, then do it multiple times, right? With intakes in different areas and exhausts in different areas, okay? All right. And by the way, I had a correction from a good friend of mine in industry that may is a term that we had used in S500 for air filtration devices over a period of time, and recommend is the update that was put into the most recent standard. So may permissive, recommend is something that is not necessarily standard of care. That would be a should, but it is the recommendation of the consensus body that developed that standard. Thank you very much. A good shout out to my good friend Darren Foote for shooting me a text as I was going through that. Thank you, Darren. If you're now kind of moving to air filtration devices that are being installed during the active drying process, now the strategy significantly changes. If I am using air filtration because I'm following that recommendation, thank you, Darren, for the installation of an air filtration device because cleaning alone wasn't effective, I have immune compromised individuals, and that's the reason why I'm installing it during the drying process. At that point, your air movement should be handling the circulation for you. All right, so I've got air movers that have an intake from one room, exhaust into the next. I'm getting good air exchange between all of my rooms already. So now there's no reason to be fancy with my air scrubber. There's no reason to have its intake in one room and exhaust in the next or use ductwork. I don't need to do any of that. What I need to do, and what I find to be most practical, is to put the air filtration device more out towards the center of the room, because what tends to happen if you've got a laser particle counter, hold me to task on this and try this. This is what I've observed, is that as soon as I get this kind of rotating airflow established around the perimeter of my rooms, what I find is that my particle count becomes much higher in the middle of the room than it does around the perimeter. That tends to be where my dust starts to settle out. So with that in mind, I tend to lean on putting my air scrubbers more out towards the center of the room once I'm in an active drying process. Okay. But the nice thing is it doesn't really matter where you put it because you've got good circulation. And if you don't have good circulation, fix that. Then it won't matter where you put it. All right. So with that said, that's air filtration. Now to close things out, just a couple of quick mentions here on some other specialty equipment that was not covered in detail in today's presentation, just because of the amount of time we have here, technically speaking, but I want to give them some honorable mentions. Electrical distribution systems. Consider the use of electrical distribution anytime you are dealing with an electrical system in a property that has any yellow or red flags associated with it. No proper grounding on your outlets. It's an aged electrical system, and you're seeing fuses and not breakers. Consider it any time that you will have occupancy, and the occupancy is going to be using those same electrical outlets and demands occupying the structure, and you want to establish your own reliable power system to manage the equipment that you're running. So lots of reasons that I would consider using an electrical distribution system. The next one down is heating systems. This in and of itself could be a whole conversation for technically speaking, so I'm only going to give this honorable mention. When you do use heating systems because you're drying in cool climates, or you're using radiant systems because you're trying to focus energy, just two real quick words of caution. Number one, I would highly, highly encourage that with fired systems, they be indirect. I highly discourage the use of direct fired heating systems for a drying environment for lots of different reasons. One, because they add moisture to the environment to a degree. We can argue about how much, but they add moisture. Secondarily, if those systems are not properly balanced, they are going to add a lot of carbon monoxide to the environment potentially if we don't have complete and total combustion. So there are a couple of red flags associated with those. Containment is something that I don't think is understood well in our industry, but it's something that should, as a specialty drying system, be considered. Anytime that you have an affected area that measures less than half of the total space within an environment, in my opinion, containment is a good way to be more efficient with your drying approach by reducing the amount of air that you're managing. There's kind of a give and take there. Anytime that we're more than about 50% of that affected area being wet, being the wet area being more than 50% of the total area within the space, the value of containment starts to drop pretty quickly. So that's kind of a litmus test that I use. By using containment, am I reducing the amount of air that I'm managing by at least half or more? Then I tend to see that containment can be very cost effective. And then finally, last but not least, it's an honorable mention is remote monitoring. It's a growing trend in industry and something that we will dedicate a future episode to here at Technically Speaking because it is starting to become a bit more prolific. So a discussion on when, how, and how to treat remote monitoring as it relates to on-site monitoring. I plan to spend a little bit more time on that today, but we are up against time. So with that, I'm going to close out with a couple of statements, then we're going to roll into Q&A. So with a couple of quick statements, first and foremost, the first thing I want to touch on is if you're not aware, CoreLogic has become Cotality. So if you see Cotality, know that what we're talking about there is what you've come to know and understand and trust as CoreLogic as we launch our new brand into our industry. Also understand and know that any of our episodes that we've had here at Technically Speaking can all be accessed at nextgearsolutions.com/webinars. Just click on the link for the IICRC approved courses, and you're going to find a whole bunch of Technically Speaking there, along with other webinars that I've hosted for Cotality in the past that are approved for your CEC credits. Next month, by the way, I'm going to divert from specific drying strategies for a little bit. And I'm going to get into project management and talk about maximizing efficiency in your project plan. How, as a restorer, do I ensure that my drying plan and my overall project plan are uniquely fit to that specific project? Right? And then how do I adjust that plan based on what I'm seeing from my monitoring? So we're going to get real deep into maximizing the efficacy and efficiency of project management. So that should be a really good episode, especially for those of you that are in the field making those decisions day in and day out about, is this restorable? Is it not restorable? And even if I thought it was restorable, is it truly restorable now that I'm not seeing results on the second day? How do I make that decision? How do I document that and justify that decision? So we'll get really deep into the nitty-gritty of just kind of the mental process of water damage mitigation. So that's where we're going to go next. And with that, we will see you all next month as we dig into kind of the mental side of water damage restoration. Take care. Have a wonderful week.